Okay, good evening, everybody. And welcome to our Friday night astronomy talk. What's up, gravitational waves? More messages from ripples of spacetime with our presenter, Hyun Lim. So my name is Siobhan Nicholson. I'm the Education Programs Director with PEEC, and I will be the moderator for today's talk. And tonight's talk is being recorded. So we're able to continue offering programming at this time because of our wonderful members and donors. So if you're in one of those groups, thank you so much for your continuing support. We really appreciate it. And I do think it's an important thing that we can continue to do during this pandemic time. Okay, so this is Hyun Lim. He got his PhD in physics at BYU and is now a postdoctoral researcher in CCS2 and the Center for Theoretical Astrophysics at LANL. His research interest is studying the dynamics of compact objects such as black holes, neutron stars, and white dwarfs to understand various phenomena in the universe, including gravitational waves, which he'll be talking about tonight. So Hyun, welcome, and I'm excited to learn about gravitational waves.
Okay, thanks. Okay, good evening, everyone, and welcome to join the talks. My name is Hyun Lim. So I'll talk on the gravitational waves. So my talk is consists in 3 parts. So I will talk on the past, which is what is the gravitational waves, how we have that idea about it, and how, what is the effort to try to detect it, and also the present. So in this talk, I would like to emphasize the recent result from the Gravitational Wave Observatory, and of course the future about the observation. So let's start from the past. So this is the somewhat schematic picture about the gravitational wave event. So we detect the gravitational wave from the merging two black holes. So black holes inspire each other, and when they merge, and then you see there's like a peak signal over there, and then after that it merged together and then turn into something called the ring down phase. So we see that signal, and then we also mentioned about that the emerging 2 black holes. So now thinking about, and then that's another picture which myself and my fellow Jonah Miller gave a talk about that the gravitational wave about last year in the PEEC. So we mapped into the PEEC planetarium and then where that gravitational wave came from. So we are also kind of missing about that the being in person, but since we are in the situation, unfortunately. So now let's thinking about that what is the gravitational waves. So gravitational waves, as I mentioned in my title, is the ripples of the space-time. So what that means exactly. So thinking about that, you go to the actually pond and then throw or some little rock or stone into the pond. Then once rock hit the pond, you will see that these ripples travel through the water. So this is exactly what gravitational waves do. So thinking about that, this one point as with the black mark, and once it has some movement or whatever, some action, then space-time itself squeeze and stretch. It's something like that. So if you see my video, I mean my talk right now, and if you have a fist, and if you like shaking like me to your friends, family, whatever, you also literally generating gravitational waves. So that means anything, any massive object in the universe, it has the motion, it generates the gravitational waves, like what we throw the rock into the water and then we see the ripples. Then we want to know that how much stretching and squeezing in the space-time. So that's some formulae from the idea of Einstein. You don't need to worry about the whole detail. So this H is called the wave strain. That's to explain how much is stretching and or compressing of the material. That's what LIGO. I will explain what LIGO means soon. Observe it. And this is some measure how much accelerated and how much fasted. and that's the distance from the source. So only the important thing about this slide is the prefactor is to the 10 to the negative 44. It's like 10 to the negative 44 is really, really, really small value. Like thinking about that, the atomic nucleus, it is about like 10 to the negative 10. We see about a billion. That's the factor 10 to the 9. It's really small value. So even Einstein's think that the 10 to the negative 4 will never see this. And I'm not the making about his comment. And in his actual 1916 paper, written in German, but it's translated, and there's some formula, and then he made a comment. In any case, one can think of A, the value of the A will have a practically vanishing value. So he's really skeptical on we can see that. And then scientists think that the some more exotic or some energetic scenario we can imagine. So if two black holes, which has the mass of the suns, they are orbiting and merge eventually, then the prefactors change slightly. So instead of the 10 to the negative 44, now it turns into the 10 to the negative 21. But it's still really, really small value. So if you were like me, I'm still thinking that, nah, that's too small. It's impossible to see that. But fortunately, we have a great fellow scientist, Rainer Wondraber, Kip Thorne, Rainer Weiss, and they think that the 10 to the negative 21, and they think that maybe we can do this. So they started thinking about that to observe this small, tiny stretching and squeezing space-time itself. So that's the some original idea about the 1970s, how we can measure it. And then note that the Kip Thorne and Rainer Weiss is Nobel laureate in 2017 about a gravitational wave observation. Unfortunately, Ron Draper passed away before the Nobel Prize ceremony in 2017. So they start to build the gravitational wave observatory called the Laser Interferometer Gravitational Waves Observatory, called the LIGO. So this first construction was started in 1994 and 5 in both Washington and Louisiana, the Livingston and Louisiana, Hanford and Washington. And then after around 10 years building, and they start to first operation run from 2002 and 2010. During this observation, there's no such exciting thing they can say. So they think that, yeah, we may need to upgrade it. So they shut down and started to do another thing called advanced LIGO. And that's the reason some people refer to LIGO as the A LIGO construction. And after around 5-year construction, they started to operate it on 2015. So that's the LIGO in the Hanford, and that's the LIGO in Livingston. So that's the some inside of the picture of the LIGO. As you can see in the previous picture, it has like a long arm, and that's the one way. So they made a almost vacuum inside to travel the light. And then there are some meter or at the end. And then this tube side is like about the human height. And then some more construction to having this make the sensitive meters to do that. So how it works. So that's the video to explain to how LIGO work. So idea is the interferometer idea. So we shoot the laser and then split it. And then light travel around the 4-kilometer arm, and there's a meter, and they reflect it. And they merge again. And due to this reflection, there are some what we call the phase difference between them. If there's nothing, that phase difference shouldn't be changed. But again, the gravitational waves is the ripples of the space-time itself. It has the squeezing and stretching our space-time itself. That means at the end of these arms, stretching and squeezing itself, that makes this phase difference. So that's what we measure about a gravitational wave through this interferometer idea. So that's the detection, what I showed into the September 14 in 2015. So two black holes inspire each other. and they merge. And the gravitational wave travels through whole universe. And it reached to the Earth. And of course, this scale effect is really exaggerated. But again, the gravitational wave is distorting our space-time itself. As I showed before, this is really small effect. So how small it is? So let's zoom into the hydrogen atom to reach to its center, proton. And this is really tiny effect. The change of distance is thousandths of the diameter of the proton. So this is really small, tiny changes. And also, gravitational wave is not really the sound, but we can make it as the sound. So that's the sound of the first gravitational wave event. Yeah, so you can hear that the like whoop whoop sound. Like first two lower tone sound is something like the sound we just observe it, and the last high pitch sound is just like a rescale it to hear it more clearly. So from this event, and of course we want to observing more, and the LIGO is not the only gravitational observatory in the world. So the first phase we called observing run first, or O1, and that's starting like 2015, and that's technically some more testing run. And then there was second run is O2, and that's another run on it. And at the end of the O2, there are another gravitational observatory in Italy called the Virgo. They also joined. And now we are getting to the phase called the O3, which is the I will mostly concentrate on. And the O3 was planned from April 1st through April 1st, 2019 through April 30th, 2020. But O3 was terminated earlier around March 27th due to the, again, COVID pandemic situation. So O3, both LIGO Virgo started, and there's another gravitational observatory called the Kagra, which is located at Japan. So they also start to join. And there are another plan called for the LIGO India around the middle of the 2025. So that's the more plans to have it. So that's the somewhat picture about the some first LIGO observation run. That's the y-axis to the mass of the black hole in the mass of the sun. So 20 solar mass means 20 times the solar mass, mass of the sun. And then that's the result from the O2. So you see that there are more black holes, and also there are one neutron star merger event. And that's the latest result, which is LIGO and Virgo collaboration recently released about like a week and a half ago. Result from the O3A, which means it's the first half of the gravitational wave observing run during the 2019 through 2020. So O1 has the two gravitational wave from the black hole mergers, and O2 has the 9 gravitational waves observation from black hole merger and 1 neutron star merger. And then O3A has the 39 gravitational wave observation from black holes and neutron star. So in total, we have the 50 gravitational wave observation now. So now let's talk on the present, what we observe and what that means. So there are 56 detection candidates were announced. So from the O3, that data technically available for the public. So if you Google the Grace 3B, and then they have some public alert. So if the LIGO and Virgo, things like that, they observe something and they make the alert about it. So that's some screenshot about I took that website. And currently they present again O3A, the first half of the O3 period from the April 1st 2019 through the end of the December 2019. So they are working on some remaining candidate, which will call be O3B. That will be announced, I think, the next couple of months. And they also released a catalog called the Gravitational Wave Template Catalog 2, which contains also first 2 observation runs. So that all the 50 gravitational wave observation contain the GWTC2. So we have the 50 things to talk, but that's too much. So I would like to emphasize something more exciting or say some exceptional discovery of those 3A. So that's the convention we make it, GW190412. So GW stands for the gravitational wave, as you expected, and 190412 is like the detection date. So 2019, April 12th. So that's how we can understand this number. So this is the first black hole collision in which the 2 black hole has widely mismatched mass. It's like asymmetry mass. So from first 2 observation runs, so mass difference between black hole mergers are almost equal mass, like 5 mass of the sun with the 5.5 mass of the sun. It's not that many difference. But for this data, the larger black hole has around the 30 times of the mass of the sun, and smaller one is like around the 8.4 mass of the sun. So why this is interesting? This can provide evidence of the higher harmonics. So what that higher harmonics means. So as I showed in the previous slide, so the idea about a gravitational wave, of course, came from the Einstein. But after that, later we find the Newman and Penrose and Kip Thorne and many others. They study on how we can understand this gravitational radiation theoretically. And they think that this is dominated by some mode called the quadrupole. And easy to understand what that means is like some musical instrument like a guitar. So you can having some picking the sound using the guitar if you touch the string. And again, it's like like a musical instrument. If you move your finger, and of course it has the different sounds from your guitar. So gravitational radiation, also like in the guitar, is predicted to also ring at the higher overtone. This is called the higher harmonics, or different terminology. People also say higher multiples. This is really, really hard to detect using the almost equal mass black hole binary because of the dominant signal is the quadrupole. So we are quite exciting to see how this will give different type of the harmonics, and then it also provide evidence of the higher harmonics, which can also test Einstein's theory of the general relativity. Use that. So another discovery I'd like to mention from O3A is like a GW190425. This is the second gravitational wave event from merging 2 neutron stars, following from the GW170817, which is the first neutron star merger from LIGO 02. And then why these neutron star mergers are exciting. So if you see the previous video about merging 2 black hole, when they merge, it just merge and emitting the gravitational wave. So that's the video about a neutron star merger. And when they merge, it's emitting materials. Like I say materials and a lot of things. So you see that at the beginning, they shoot what we call the relativistic jets, which is really, really high speed. Like going back to the video again. And after that, it has some material remaining around the neutron star, which you call the accretion disk. And as you can see that this afterglow also changed their color because of the neutron star has some composition inside of it. So from this single neutron star merger, and LIGO detect the gravitational waves. And then, as I say, this is something like a really energetic event from this merger. It's also called the gamma ray burst. So there are some satellites outside of the Earth. It's called the Fermi and interstellar satellite. They also detect the gamma rays. And after that, they also emitting X-ray and some few visual optical signal that was detected like many different places where you see that there are these small dots. And after that, VLA, which is located in New Mexico, detect the radio wave. So like one single event, we can literally use all the possible astronomical astronomical observatory to understand this event. And then this is just some example about where this is located. I just pointed out this LIGO because we are talking about gravitational waves, but also there are some satellite out of the space, and there are multiple different stations into the Earth. So that detect a different signal like gamma rays, X-rays, radios, and now this is called the multi-messenger astronomy. And another thing is like why this is also interesting and why we would like to understand this such an event with the different various channel, because neutron star, we believe this is the main source of the creation of the gold. So this is the plot. This is called the all process nucleosynthesis. You can easy to think that when they merge, they have a really high density and energetic event have a nearby depth. They also change the element. So in the universe, if you're going back to some chemistry book, you see that there's some periodic table, and you have like different elements we can find. And from the Big Bang, we know that the other hydrogen, and after this like nucleosynthesis idea, they synthesize the helium. We know that the lithium, like platinum, uranium, etc., a bunch of different things. But after the iron, because of the iron is so stable, it is really hard to having heavier than ion element naturally. Means we need some engine to create heavier element in the universe. There are some different multiple ideas how these heavier elements are generated through various really energetic astrophysical phenomena, and neutron star merger is one of the events. So the plot you are seeing right now is called the mass fraction and mass number plot using the all-process nucleosynthesis. And these green dots, what we are called the solar abundance, like how many material abundance in our solar system. And this blue-purple plot is some all-process nucleosynthesis data from the neutron star merger using simulation. You see some peaks that matches well with the solar abundance. And then mass number on like 190, which is this peak. This is the gold. So that's the reason. If you remember, you may see that some people also describe this neutron star merger as the golden binary. So neutron star merger can provide really interesting, say, some experimental platform to understand the like heavier element formation and also different astrophysical signatures. And another discovery I also want to mention is called the GW 190521. This is the binary black hole with total mass over the 150 times of the mass of the sun. So this is the some plot. So you see some black hole mergers, as I mentioned in previous, and this is really larger than compared with the other things. And again, like why this is interesting, and this is some highlighted picture. So that's the reason at the previous plot you see that the like one black hole is like above the top from this stellar graveyard picture. And why again this is interesting. So astronomer and astrophysicists classify black hole with respect to their mass. So there are some primordial black hole. We believe they're really tiny mass black hole that might be created from beginning of the universe. And there are something called the stellar mass black hole. The formation of the stellar mass black hole, if some star has really big mass, larger than the sun, at the end of their stage, and due to they now cannot. They're using, easy to say, they use the all their fuel, so they now gravitational collapse into themselves. Then they have like explode. That event also something called the supernovae. So stellar mass black hole is something like 10 solar mass etc. or so. And then some mass black hole is like 100 or like 1,000, tens of the thousands of the black hole. We are called the intermediate mass black hole. And then some black hole mass is like 1,000,000, like 1,000,000,000 mass of the sun. That thing we are called a supermassive black hole. And then supermassive black hole is interesting. It's already observed by the idea to see the how stars move around center of the galaxy. This is the Sagittarius A, around the 26,000 light years away, and mass is like a 4 million mass of the sun. This is the video from the UCLA group. That's how they confirmed that the yeah, we have the supermassive black holes in it. And then I mentioned that the black hole is classified by their mass, and that also implies that the black hole mass can also determine the size of the black hole. So thinking about that, the stellar mass black hole has like a few times of the mass of the sun. This is really, really small. It's like a few kilometers about it. And another way to see supermassive black hole recently about really exciting Event Horizon Telescope effort, we now picture the shape of the black hole. That's the first picture from the Event Horizon Telescope. That's how the size of the supermassive black hole we think. So like this is our solar system. Now Pluto is not even our solar system. The black hole is larger than our solar system itself. So you can imagine that now the range of the mass in terms of the size of the black hole. So now we know that the existence of the supermassive black hole. We also know that there are some stellar mass black hole mass orange like a 10 solar mass, something like that. But we really don't know existence of the intermediate mass black hole and also their formation channel. And by the way, this is the award by the Nobel Prize in Physics 2020 by the Genzel and Guess about discovering the supermassive black hole. And I think that HN will give a show about this event on the early December. So that's the big mystery right now. So as I said, we know that the existence of supermassive black hole, existence of the stellar mass black hole, but we really don't know how this supermassive black hole forms. And also, as I said, the intermediate mass black hole exists. The now answer is yes. But again, we only have one data point, and also there are more wide range of the mass. So that event detect the 150 mass of the black hole. But we also want to know that there are thousands or like 10,000s of the mass black hole. So that's the reason this is the really interesting discovery. Now we are seeing that there are like hundreds of the solar mass of the black hole. We only imagine that in theory. Then another one is called GW190814. That's the first collision that involve an object in the mass gap. So I will explain what mass gap means between neutron star and black hole with wide mass difference. So that's the two interesting aspects in here. First, some object is called the mass gap. And also another thing is like a mass difference between this black hole and this mass gap object is really large. So the black hole size, this is around the 23 mass of the sun. And then this question mark, or say mass gap, is like around 2.5 times mass of the sun. So if you see that stellar graveyard picture again, and you see that there are some question mark here, and that's around the 23 mass of the sun, and merge into the one black hole. So what is the mass gap? So mass gap is the some hypothetical mass around like the 2.5 through like a 5 mass of the sun object. So using the theory, we know that there's some upper limit about that neutron stars. And also by the observation, we know that there's some lowest mass of the black hole. So lowest mass of black hole we can think or see right now is about the 5 times mass of the sun, and neutron star mass limit is about again 2.5 or higher or a little less. So question is, so okay, what is the object between 2.5 and 5? So that's the one interesting aspect. Now we know that there is something exists in the mass range. Now we want to understand this is the nature of the sun, what we call the hypermassive neutron stars, or some other tiny black holes. So that's the another exciting thing to see. And then I'm not going to talk too much about these two events, but I also want to draw the attention and also another convention I want to say. So this is GW 190425, and they have another number 15, 20, and 55. The reason people put that number after this date because we have a multiple candidate on the same date. So that's the time in UTC. So that's the 15, 21, so hours, minutes, and second. So that's the reason we have like more numbers. I'm pretty sure eventually people will change their labeling convention, but that's the current convention, what LIGO people do. That's the possible low mass event of the neutron star and black hole merger. This is something like 6 times of the mass of the sun black hole with around like 2 times mass of the neutron star. And then another event called the GW 170924. This one is the again a possible lowest mass binary black hole merger. That both black hole with both black hole merger, they will exceeding light above like a 6 mass of the sun. So this is really tiny compared with the 150 times mass of the sun black hole merger. So now I mentioned a lot in some detection about the event. Then what we can do about it. So one possible interesting thing, and that's the all the physicists want, we want to test general relativity. So this is I just took the screenshot from the gravitational wave template catalog and their paper, and as you can see, there are way more events among what I explained so far. And then we perform some tests. I'm not going to explain the whole detail. And then we have like 8 different ways to test general relativity. It's something like we can check the row frequencies in spiral high frequency merging down part of the waveform are consistent with the Einstein theory of general relativity. Also, we also see what we call the spin, means the like rotating black holes is the consistent with the theory of the general relativity. And then we also measure the a final black hole ring down phase. Also, this is the consistent with the general relativity. As you can see, like a check all the thing. And then after careful analysis, and then so far the conclusion, we find no evidence for the deviation from general relativity. So this gravitational wave event is really great test bed to check the Einstein's theory of the general relativity. And even further, we can test beyond general relativity. General relativity is beautiful, perfect theory, but it is not complete. It cannot explain the quantum nature of the universe. It also cannot, so when we mix this like a classical general relativity with the quantum theory, there are some unexpected situation happen, such as information paradox, etc. And that's the reason theorists explore the beyond general relativity theories, like quantum theory of the gravity, possibly string theories, group quantum gravity, etc. And also, what if we impose higher dimensional, more than 4, etc. Like there are a lot different theories people impose, and of course, most of them is really hard to test in the nature. But again, the event from the gravitational waves are really exotic and energetic that also provide great test bed to test the theory. And that's the one simulation which is part of my work, is to see the gravitational wave form with the hypothetical particle called the axion. So this K0 means the like how big axion in that theory, and then we perform the black hole merger and then extract how gravitational wave signal look like. So except this value, I keep the all other environment are the same. I using the same mass of the black hole, same initial distance, etc. And as you can see in this figure, if we have the quite highly dominate axion, you see the gravitational wave signal is way different than the smaller one. So if LIGO or Virgo or some possible future gravitational wave detector can detect this kind of this, that implies that we have some indirect evidence that there are certain objects that contain this hypothetical particle in it. So that's another people are looking a lot to understand it. And as a consequence, again, using the gravitational waves, people now started thinking about find a new particle. So what I mean by find a new particle is like a fundamental particle in the physics, like an electron, proton, and even more. Electron and protons is consistent of something called a quark, and quark also consistent something called again, this is more hypothetical, like strings or some other fundamental particle stuffs. And then most of them, this is some several different picture from the Large Hadron Collider from Switzerland. It's called LHC. And you may see that this kind of the picture when they accelerate into hadron and they collided. And there are some many different signals came out, and then they analyze masses, energy, etc. to understand, to find the particle. And this is the place where they confirm it's called the Higgs particle on it. But now we can use the black holes, to find a new particle. So this is the example about the highly rotating black hole, or say highly spinning black hole, and around some hypothetical, again, some cloud. And you can see due to the black hole that they are like emitting some waves. And then use that, and we know that and this figure shows that like a LIGO Voyager explorers and different types of the gravitational wave detector, and then some mass or say energy of the particle, and there's the detection strength and frequency band, and that they might be pinpoints down to find this new type of the particle. So this gravitational wave helped to identify signals from the new particle. So which is like we are entering new era of this particle physics too, not just astrophysical event. So now I'm sure that the several exciting events and also what that means and what we can learn from that. Now let's talk about the future. So this is the range of the gravitational wave. As I said before, gravitational wave, we can thinking about that your waves, like a sound, means it can have different range of the frequency. So this is our first black hole merger event, GW150914, and that's the one plot, and that's what we call the sensitivity curve, which means what is the range of this squeezing, stretching into space-time this detector can observe. And of course, we can think more. There are multiple different sources that emitting gravitational wave and that we want to detect. So for example, some core collapse supernova, and also some extreme mass ratio in spiral means that the difference between two black hole mass is really large, such as like one black hole mass has like 1,000 times of the mass of the sun, and then another one is like 1 times mass of the sun, something like that. And also some lower frequency band is called some supermassive black hole binary, means like millions or billions of the mass of the black hole, then they're binary and merging it. or some more astrophysical relevant phenomena is called like the two galaxies merging each other, and also some massive binary and different thing. And again, I just put this like Virgo, LIGO, and Kagra, which is only can focusing on this type of the signal. But of course, now we are want to having way more than that. So that's the some planned ground-based gravitational wave observatory, Einstein Cosmic Explorer, and the Einstein Telescope that also aim to the like this band. And then there are some, I will show the picture later, some space-based gravitational wave detector. Means we want to detect gravitational wave from the outside of the Earth, not ground-based. It's also planned, and there are some different radio wave or some observatory like a GMT, etc., to detect like a different ways to observe the gravitational waves event. So this is the one idea, what I mentioned, the space-based gravitational wave observation. The concrete plan right now we have is called the LISA. LISA stands for the Laser Interferometer Gravitational Wave Observatory. The basic idea is like this. Earth is rotating around the sun, and then we shoot the 3 satellites that they make this triangle shape, and then they follow the this orbit, Earth orbiting the sun. And of course, each other also rotating. And then once the gravitational wave signal came, and then this is the exactly same idea, how this line is stretching and squeezing. So this is, you can easy to think that you put the LIGO into the space in triangular shape. So that's the plan for the future event. So it will be launched hopefully 2034, which is around 14 years from now. So once it's settled and then start to observing, then we can hear way more different gravitational wave sound or event from this. And then you can also help them too. So I'm talking about that there's some large collaboration, but this is not only some few numbers the professional scientists work. So two interesting effort is called the Einstein at Home. This is the idea about using your computer to having some data analysis. So since the data we get from the LIGO is really large, and we want to using the technique called the cloud computing to somewhat classify and understand the signal. And another effort is called the gravity spy. The most important signal is the glitch. Of course, you see that there's some glitch happen at the some figures I showed before. And then again, this LIGO is like really sensitive. Like it can measure like a different the distance, the difference of the distance LIGO can measure is thousands of the diameter of the proton. So literally, if you go to the Livingston and Hanford when both LIGO observing, and if you just like I don't know, clap or like yell it in front of the LIGO, then LIGO also will your sound as the glitch. So glitch classification is important project to understand gravitational wave and also decouple a lot of noises. So again, it also costs a lot of computational power. So also using your computer or your computational power to have it. So if you go to search like Einstein Get at Home or Gravity Spy, then you can see how you can do that too. Okay, summary. So from the past and present and future, we can now see and also listen to the universe with the new eyes and of course the ear, called gravitational waves. As I said before, gravitational waves offer really, really new insight into many fascinating astrophysical phenomena, including understanding how heavier elements formed in the universe, what is energetic events such as gamma ray burst, kilonova happened, and to understand the theory of the general relativity and also beyond theory of the general relativity and find the new particle, etc. And this is still ongoing effort. So we are about releasing the data we can have for go, and people like digging into the data to understand like a lot of different stuff. So lots of mystery will be soon unraveled. And also we are the scientists. We really love the answers, but I'm pretty sure we love more questions. That there are many different unknowns. So that's the really exciting future we can say. And thanks.
Okay, thank you so much, Hyun. We do have a couple of questions that have come in from the audience. And so one of them is, you mentioned a neutron star merger, which could be detected with all kinds of different astronomical detection systems. And so the question was, do all the signals come in at the same time, like the gravitational waves, X-rays, radio waves, etc.?
No, that's really good question. So I didn't mention it specifically. I should be confessed. Unfortunately, the O3 event didn't detect after gravitational wave, or something we call the electromagnetic signature. So that's the reason these gravitational wave events are important, because that's the first signal they can detect. So thinking about that, you have a hotline. So once LIGO detected, and then they can ask, hey, we think that we see something. So satellite, point your direction to there, something like that. So gravitational wave is once observing gravitational waves, then following event is gamma ray. About, I think that, I forgot the exact number, say about a few hours. Then follow up the X-rays and visible events that even lasts like a few days, and also even few weeks. We see that the like a radio signal from the VLA. But that's the kind of the funny story about it. So before LIGO releasing their data, and then we can't say that we detect neutron star merger like about the 2017. But the funny thing is like that we told to the world, we think that we see something. Please, other fellow astronomers, can you also point it out? Then everybody exciting, oh, that's the neutron star merger. Then, oh no, we can't tell you, but you should see that portion of the sky. And then then we now release that's the neutron star merger. So that's the one of the good thing about a gravitational wave astronomy. We can have a really great hotline to where we need to look at the sky, because universe is really large and we need to localize the sky.
Okay, thank you. All right, here's another question. When two black holes merge, the resulting black hole has a mass less than the sum of the two, and the rest is radiated as gravitational waves.
Yeah, exactly.
Okay, so what determines the mass of the product and the amount of radiated energy? Is it a geometry? Is it the spin, or is it something else?
So that's the another terminology called let's begin. So think that the two black holes orbiting each other when they merge, and then the final mass is less than sum of the two original mass, and then the a remainder mass, of course, that is emitting about that the gravitational waves, and then that's to determine the how many masses we have. This is what we determine is called the chirp mass. So this is the so that determines the some leading order orbital evolution of the system, like a spiral to a black hole, as the result of the energy loss from the emitting gravitational waves. So gravitational wave frequency is determined by orbital frequency and chirp mass. Orbital frequency, and then chirp mass also determine the frequency evolution of gravitational wave signal emitting the binary spiral. So that's some terminals we call it chirp mass. And there's some formula to calculate it.
Okay, Galen, I am going to ask you if that answered your question, and you can just send a message in the chat if you have any follow-ups or anything. Okay, let's see, we have another one. Did the list show an even more massive black hole collision that produced a black hole with a mass of over 240 solar masses?
what 240 solar masses?
Says, did the list show an even more massive black hole collision that produced greater than a 240 solar mass black hole?
Well, so okay, so like where's the big picture? There we go. So like the plot I showed, I mean the list of the thing I showed. So I think that you mentioned this. Yeah, here we go. So that's the so easy to say. That's the mass of the two original mass, and you see that this like m, like some scripting m. That's the something called the chirp mass. So I'm saying like some masses about some exact number, like a 20 times the mass of the sun, or say like 5 mass times the sun, etc. Blah blah blah. But of course, this is not the really the correct way to say. Like as you can see, there's like plus minus sign. There's some like interval between about it. So I believe the largest mass is the LIGO releasing is the like 150 mass of the sun. Yeah, I didn't explain like whole detail this thing really well, but yeah.
Okay, so Galen has sent back a sort of a related question to his earlier question about the masses of the black holes. So if you have like two situations, right, where black holes are colliding, would the product mass always be the same? Or would there be like, could there be different circumstances which would cause more or less energy to be radiated away as gravitational waves?
Well, like
so if you have,
yeah, go ahead.
Go ahead.
Yeah, that's the question. So if I get it your question correctly, so you mean that the once two black hole merge and then some of the final mass of the black hole plus radiating energy should be the same? That's the question, or?
Well, no. So you have these two black holes and you collide them together. Is the resulting mass always the same? Or are there some cases where more energy is radiated away, resulting in a smaller mass of the product, and some cases where less energy is radiated away, and so you have a larger resulting?
So that's the another thing is called like when people actually calculating the like this called some chirp mass, and there are some another factor called like some mass ratio stops. So yes, assume that we have an exact same situation, and by our understanding, it should emitting same amount of the gravitational wave event. But if they have like a different exotic scenario, like again the mass ratio is really high or like a highly spin online, I didn't mention also spin effect into the gravitational wave, then emitting gravitational wave amount can be different. And then again, that's the reason gravitational waves are important to understand nature of the black hole, like how spin and how mass and what's the system, etc.
Okay, so it could be that things like spin and things could make a difference.
Yeah. And also recent study also
like,
mentioned that the charge of the black hole could impact on this black hole event merger too. But that's the really preliminary study people currently looking at.
Okay.
And that's also another interesting question about that there is called the no-hair theorem. So black hole is determined by only three components: mass, spin, and charge. So that's the some theory we pose, but also that caused the issue that then how about some other information when black hole actually originally created, and or if I throw my laptop into the black hole, then all the information that laptop has, where are they? So that's what I just briefly mentioned about this information paradox. Information is losing inside of the black hole, but information must be conserved in the quantum theory. Yeah. So that's again another reason why gravitational events are interesting to see.
Okay. Cool. All right. So someone is wondering if gravitational waves could merge in a way that forms a black hole?
During the gravitational, yes, that's the one thing we also want to see, that like supernova, the one formation channel when black hole formed. So we also want to detect the gravitational wave from the supernova.
Okay, and she's wondering how black holes were formed in the early universe.
In the early universe, okay, I'm not the really expert on that aspect, but the only thing I can answer is like, this is the idea is called some primordial black hole, when the mass of the black hole is really, really, really tiny. So at the beginning of the universe, or say when Big Bang happened, people think that there are certain, to determine make the black hole is kind of the simple process. If you squeeze it mass into the really, really small tiny region, that became into the black hole. That means if someone squeezed myself into really, really tiny amount of the size, is I don't know, like 10 to the negative 15 or really tiny, then I will become a black hole. So that's the some basic idea, like primordially when a universe was created. And that might be a possible case. Some people also call it, this is kind of the black hole seed, like a really, really tiny amount of the mass, or say some mass that somewhat created like a really tiny amount of the region naturally. But again, we never detected primordial black hole yet. So that's the more some speculative description.
Okay, thank you. And just so you guys know, next week, Rick Wallace will be giving a talk on primordial black holes at the same time next Friday. And so he's going to be talking about how those are formed and if LIGO has seen any signs of any. Okay, so tune in next week for more on that topic. Okay, let's see. We have just one more question, which is, can you remind us when the next observing run is slated to start?
Originally was 2022, once they shut down. No. Yeah, I think the 2022. But again, due to COVID pandemic, the region LIGO shut down. So maybe I'm going back to the old figure. Oh, there we go. Nope. Okay, so you see that I didn't explain it. You see like these numbers, like 80 MPC. MPC means the megaparsec. This is the unit of the distance, like 100, 105, 160, like something like that. So another region shut down the LIGO, or say having the observation period, they also want to increase detection range. So based on the target detection range, once LIGO reached that detection target range, and our expectation, we will see black hole merger every single day. So 04 was planned, I think 2022, even that figure shows that the end of 2021. But this is somewhat undetermined now due to COVID pandemic. So answer is maybe 2022, middle of the 2022, like a year maybe behind it from now, but I don't know, yeah. Sorry, like COVID also impacts scientific research to a lot right now.
Okay, and then one more question that just came in. What fraction of the energy in the universe is in the form of gravitational energy?
What fraction of the energy in the universe form of the gravitational wave? Wow, I never thought that. Okay, so then I need to coming back to the universe itself, because like as she said, there will be talks on the like a dark matter thingy into the next week, because our belief like around almost how many percentage, like almost 95% of the universe are known, and that might be consists of the dark matter and dark energy, which might be also related to gravitational wave. That's the people hope to find you like a dark matter type of using the gravitational waves. So let's think that the 5% of the universe that we actually know, like consists of the matters, like stars, like planets, black holes, something like that. So what fraction of the energy of the universe could be a gravitational wave? And I definitely can say that less than 5%. But the speculative calculation So we believe that there are like 1 trillion of the galaxies, and then each galaxies should be owns that the supermassive black hole, and the rotating black hole should also emitting gravitational wave too. So 5% among, yeah, I don't get the number correctly. Maybe I'm pretty sure I'm wrong. I think that among 10 to 20% of the 5% should emitting that energy into the universe. So around, I think that less than 0.5% of the energy of the universe could be gravitational wave, but yeah, I don't know. That's just my quick calculation in my head. That's interesting to think.
Okay, cool. Well, thank you so much, Hyun, for that talk. And then, as we mentioned, stick around next week to hear Rick Wallace talk a little bit more about primordial black holes. We also have a couple of other virtual learning opportunities on the slate for next week. We'll also have a talk about turkeys and a citizen science training opportunity. So find details of all of these on the PEEC website, peeknature.org/events. And Hyun, thank you very much for your talk, and all of you, thank you very much for your attention. And we hope you have a wonderful weekend. Okay, thank you very much.
Thanks.
Bye.